Okay, so let's take a look at some solids now. Specifically, the different types of solids, and we'll get into each one very specifically. And then we're going to take a look at metals and how metals work. So there are two broad categories of solids: crystalline solids, which have a very organized structure, and amorphous solids, which are disorganized. Amorphous means without shape. A, without, morph, shape. So for crystalline solids, we have what's called a lattice, and the lattice shows the 3D arrangement of the different particles. Okay? They're made of small repeating parts called unit cells. The way we determine the structure of a lattice is by something called X-ray diffraction. X-ray diffraction is a process whereby we can fire X-rays at a crystal, and the nuclei of the atoms in that crystal diffract or bend the X-rays in a particular way, so that when those X-rays are then detected, the pattern that they form corresponds to the pattern of molecules or atoms in the crystal. It's kind of a cool process. So we have ionic solids. Ionic solids are ionic compounds. They're crystalline. And at each point in this lattice structure, we have an ion. Okay? We have molecular solids. These are molecular compounds. In other words, the molecules, the atoms in the molecules are covalently bonded, and at each point in the lattice you'll have a molecule, an entire neutral molecule instead of an ion. And then there are atomic solids like metals, nonmetals, noble gases, in which case the points in the lattice are occupied by single atoms only. Metallic solids are delocalized covalent bonds between the metals. We'll see what that looks like in a minute. There are network solids, which have strong covalent bonding between the atoms. And then there are the noble gas solids, group 8A. And what holds them together are London dispersion forces, because they're stable, so they don't form atoms and they don't bond to one another. So this is table 10.3 from your text, and one of the images that shows you an example of each of the different types of molecular solids. So atomic solids. So we have an atomic solid, a network solid like diamond. We have sodium chloride for ionic. We have ice for a molecular solid. So metals exist as crystalline solids, which is kind of weird to think of metals as a crystal. But in fact, the metal atoms, if we kind of view them as spheres, they're packed together in a very regular, ordered arrangement. Now they get as close as they possibly can. The closest you can get, 12 spheres, and you can try this if you have 12 spheres of equal size, the closest you can get them to one another, you'll have one sphere surrounded by 12 other ones. There are 6 in one plane, and then 3 in the plane above that, and 3 in the plane below that. It looks sort of like this. So this red atom in the center, that's the atom that we're looking at. And the numbered spheres are the 12 closest neighbors. They're all in contact with that one red atom. So we have 6 around that atom directly in the plane, and then, so that's numbers 1 through 6, 7, 8, and 9 are above, and 10, 11, and 12 are below in a little group of 3, and they're all in contact. You can build this if you have, like I said, 12 spheres. You can sort of put it together, and you'll see that they're all touching. That's how metals arrange themselves. It's technically called hexagonal close packing, where the atoms packed together. Well, how do they stay together then? If they're neutral atoms, what's keeping them together? Well, this is something that's a rather unusual property of metals. It's metallic bonding. Since you're talking about metals, and metals generally don't have very many valence electrons in their highest energy levels, the open orbitals up there can overlap each other, and they can allow the valence electrons of metals to sort of freely roam around between these atoms. And that's what metal bonding is. It's these solid positive atomic centers surrounded by a sea of electrons. And so the more positive the metal ion is, the more electrons are in this sea of electrons around. And that sea of valence electrons holds the other atoms together, but it also gives metals their unique properties. Okay? So the roaming electrons form a sea, and that allows for the metal atoms themselves to move with respect to one another very easily. Now, you might have to apply some force, but you can cause a metal to deform by hitting it. That's what malleability and ductility are. Since bonding is omnidirectional, you can change the orientation of the atoms to one another in space, not just in a specific direction, but in any direction, and they'll stay stuck together. So layers can slide past. The other advantage to having this sea of free-roaming valence electrons is that electrons can pass through metal very easily. So if you have all of these positive metal centers separated by these valence electrons, and you put electrons in, that's all electric current is just a stream of electrons. You put them in, and they're just going to kind of work their way through and push electrons out the other side. There will be some resistance to this, and so all metals resist electric conduction a little bit, but not very much. And certain metals don't resist enough to make any difference whatsoever. Things like silver and gold conduct electricity extremely well. Now, another thing that we can do with metals is we can form what are called alloys because of this metallic bonding. So an alloy is a mixture of elements that have metallic properties. Normally they're all metals, but sometimes you will have nonmetals in there. We have what's called a substitutional alloy. A substitutional alloy, you replace some of the metal atoms of one metal with metal atoms of another metal. Okay, and it works best when the metals in question have similar sizes, like copper and zinc, for example, are right next to each other on the periodic table. Their atomic size is very similar, and so we can replace some copper ones with zinc. The other type is called an interstitial alloy. When you have smaller atoms that you want to include in there that are very small compared to the metal, you can put those smaller atoms in the spaces that are between the metal atoms. There are tiny little spaces, even though they're all touching each other. There are little places where we can put other atoms. So if there's a large difference in sizes, you'll form an interstitial alloy. Some examples of that would be brass and steel. So brass is substitutional, where we've replaced some of the copper atoms, about a third of them or so, replaced by zinc atoms. And then steel is an interstitial alloy, where we put some carbon atoms in between the iron atoms in the structure. So that actually it increases the strength of it, the hardness, and it makes it a little bit less malleable. Now, as far as the other types of solids, network solids, molecular solids, and ionic solids, we want to understand a little bit about their properties. So network atomic solids are bonded by strong covalent bonds, and they're viewed as one large molecule. Usually they're very brittle. They're not good conductors because the electrons are all bound up in bonds. Graphite is an exception to this in some ways, where you have very strongly covalently bonded atoms in sheets, 6-member ring sp2 bonded sheets of carbon atoms, but between them the pi electrons in an sp2 bonded carbon, the free pi electrons, actually form this delocalized sea of electrons between the layers. So in the sheets, the carbons are bonded to 3 other carbons, and they're sp2 hybridized, 120-degree angles, hexagonal shape, but the 2 p orbitals that are unhybridized form this network of pi bonds. The layers themselves are very stable, but between the layers, the pi bonding between the layers, pi bonding is generally less stable and easier to break anyway. And so what that means is that these layers can slide past each other. That makes graphite a very slippery substance because the layers will slough off past each other. It also allows these pi electrons become delocalized, and it allows electricity to flow through graphite really, really well. So graphite conducts electricity for a non-metal better than some metals. Now, another possibility for carbon, though, is a true molecular network solid where the carbon atoms are covalently bonded in sp3 hybridized form in a tetrahedral shape, and you get this very regular, strong arrangement. It's much harder to break. Graphite has good strength if you try to break the layers, but if you try to slide the layers past each other, there's not a lot of strength there at all. Diamond is strong in all directions. For molecular solids, we have molecules at each lattice point. And the stronger the IMFs, the stronger the solid will be. But in general, these IMFs are not as strong as covalent bonds. So the molecules stay together, but they're held together by their intermolecular forces. The bigger the molecule gets, the stronger London dispersion forces get, because the more electrons you have and the more nuclei you have. If you have polar molecules in this solid, then they're going to be much more strongly attracted to each other, dipole-dipole interactions. So examples of molecular solids would be something like sulfur or phosphorus. Those are atoms that are attracted to one another. Carbon dioxide as a solid, dry ice. Weak attractions between the carbon dioxide molecules, so dry ice turns back into a gas very easily. And you can see some examples of, in 10.6, some atomic separations. You can see that they're fairly close to one another. Now, ionic solids are very stable. They have very high melting points because the ions are very strongly attracted to one another in this lattice. Strong electrostatic forces. The larger ions will get together in close packed form. Smaller ions can fit in between them. Okay? So if you have something like sodium chloride, where chloride is very large, the sodium atoms will fit in the spaces between the chloride atoms. This is a table 10.7 from your text, that shows some properties of solids, different types. It's a good one to look at to kind of summarize what's in this lecture. So take a look at it, make sure you've taken good notes, and we'll learn some more about the behavior of solids in future lectures.